In this video, we are going to begin with fundamental discussion and concept in convolutional codes. So convolutional code is a type of channel coding. When we say channel coding, the basic aim of channel coding is to provide error detecting and error correcting ability to your code. So in addition to message bits, we generate extra bits which are called parity bits. So in convolutional coding also, we will append parity bits to the message. The typical advantage of convolutional code is usually when you have live streaming or in the applications where the delay needs to be minimum. We have discussed linear block codes and we have so far discussed cyclic codes, typically BCH and RS codes. So if you recall the method of code word generation, if it is linear block code, you generate code word by multiplication of message and generator matrix. And in case of cyclic code, we generate a code word polynomial using multiplication of message polynomial and generator polynomial. The basic requirement in cyclic code and LBC is you need to buffer the entire message, and once the entire message is stored, then only we can proceed with multiplication either by generator matrix or by generator polynomial. So that particular disadvantage will generate the delay in practical situations where we need to wait till the entire message block is buffered. Now in convolutional codes, this particular drawback is overcome. We are going to implement convolutional codes with the series of flip-flops, which is typically shift register, and as and when we receive the input bit, we are going to generate the output of a convolutional encoder which will have parity bit included in this. So there is no delay involved for buffering of the particular message. As I discussed just now, we are going to implement the convolutional encoder using flip-flops. So one way of visualization of convolutional encoder is again with the help of FSM, which is finite state machine. There are different representations of convolutional encoder which we will see subsequently. So let's begin with the fundamental concept of convolutional encoder. If we have m stage of shift register and we have n mod 2 adder, which are actually XOR gates, and then you have a multiplexer to select one of the outputs generated from the convolutional encoder. So if you apply L bit of message sequence, then the encoder will produce n into L plus m bit of code sequence. Right? Again I repeat, m is number of flip-flops, n is number of adders, and if you apply L bit of message, then the output code word will be n into L plus m bit. For example, if I have 3 stage, that is m is equal to 3, then if I have 3 adders and if I apply 5 bits of message, then the length of the code word will be 3, which is number of adders, 5, which is L, and m is again 3, so 5 plus 3 8 into 3, which is 24. So we are going to verify this particular relation with the help of encoder, which we will discuss shortly. So what will be the code rate? What will be the code rate given by the convolutional encoder? It will be L upon n into L plus m, because we know code rate is given by input bits upon output bits. So I am applying L bit of message sequence, so that will be input, which is numerator, and I am producing n into L plus m bit of code word. So my denominator is n into L plus m, that is R. Now in practical situations, your capital L will be much greater than m, because we are going to discuss a convolutional encoder, typical convolutional encoder, where m will be 2, and practically also it is proven that 8 stage of shift register or 9 stage of shift register will be more than sufficient to suffice the practical applications. So naturally the capital L will always be much greater than m, because practically proven m will be around 9. So in that case, L plus m is approximately equal to L, and I get R is equal to 1 upon n. So that will be the code rate of a convolutional encoder approximation. If you go with the exact formula, then the formula is L upon n into L plus m. That will be the code rate. Let's go to the next part.
Now
there comes another basic definition of convolutional encoder, which is the constraint length. Now to define the constraint length, let's see the very basic convolutional encoder, which is covered in most of the textbooks related to information theory and coding. So how many shift registers we have? Here we have 2 shift registers and we have 2 adders, 2 XOR gates, and input is applied here. And we are taking 2 outputs, one from the upper branch and one from the lower branch. So for every input bit applied to the convolutional encoder, we are producing 2 outputs. So how the convolutional encoder is specified? It is 1/2 convolutional encoder. What is 1? How many bits of input you are applying at a time? So I am applying 1 bit. And how many bits I am getting as the output of convolutional encoder? 2 bits. So this is 1/2 convolutional code. We have 2 stage of shift registers. So we define a very important parameter of convolutional encoder, which is called constraint length. Now the constraint length of a convolutional encoder is actually number of times your input bit influences the output. Right? Again I repeat the definition. Number of times your input bit has contribution in producing the output. Number of times it influences the output. So if we consider our case, so when the input is applicable here, when the input is applied here, I am getting the output. See the upper XOR gate, it has 3 connections from the input, then output of first flip-flop and output of second flip-flop. Similarly, the lower XOR gate has 2 connections, input and output of the second flip-flop. So whenever input is applied here, it will definitely affect the output. Then the input will pass to the output of the shift register. It will again have contribution in generating the output, and when the input comes at the output of the second shift register, it will again produce the output. So number of times it affects the input are 3. So input is affecting 1 time here, second time here, and third time here. So 3 times the input is affecting the output. The constraint length of the convolutional encoder is 3. There is one more equation which is given in most of the books. The constraint length is m plus 1. What is capital M? Capital M is your number of flip-flops. So in this case there are 2 flip-flops. So 2 plus 1. So my constraint length is 3. Right? So m plus 1 is also equation of the constraint length. But to understand the constraint length, what is the meaning of constraint length? Number of times your input affects the output. Right? So this convolutional encoder is 1/2 convolutional encoder, which has 2 adders and 2 shift registers. Now let's move forward. So I am taking again the same convolutional encoder and let's verify the operation of this. So m is equal to 2. What is n? Number of flip-flops. N is equal to 2. What is n? The number of XOR gates. And let the message applied is 1, 1, where L is the length of the message. So I am applying 2 bits to this. Right? So what is the output? L plus m into n. So 2 plus 2. What was length of the message is 2. So 2 plus 2 is 4. 4 into 2 is 8. So 8 will be the output. Now how we get this particular output? So this table will explain this. So this is operation of the convolutional encoder. So let's assume that your system is at rest. So output of this flip-flop is 0. Output of this flip-flop is 0. And then you have final outputs from the convolutional encoders. They are also 0. So initially everything is at rest. Now I am applying the first message, which is 1. So now when I apply 1 here, the upper output will be 1 because this XOR gate will have 3 inputs. This is 1, this is 0, and this is 0. So that output is 1. Lower flip-flop will get 2 outputs, 2 inputs, which is again 1 and 1. So that output is also 1. So I get output is 1, 1. That is my first output. Now that is the first clock cycle. Now in the second clock cycle, this input will move to the output of this particular flip-flop. So at this point I have 1 now, and I apply the second input, which is also 1 here. So I have 1, 1 here, and I am applying the second input. So what is the output of the upper branch? Now this XOR gate got 3 inputs. Out of that 2 are 1s. So this particular output will be 0, and the lower XOR gate is getting this 1, which is the applied input, and this output is still 0. So 1 XOR with 0 is 1. So my output will be 0, 1. So my output is 1, 1 in the first clock. Output will be 0, 1 in the second clock. Now you apply the third clock. Now the question is, what will be the input in the third clock? So here comes very important point. Our constraint length is 3. So we need to append 3 minus 1. So 2 zeros to the message. So your actual message will be considered as 1100, because when the input moves inside the convolutional encoder, this terminal cannot be kept floating. So I have to apply 0 here. So how many such zeros I am applying here? I am applying 2 zeros here because the constraint length is 3. So if the constraint length is m, I need to apply m minus 1 zeros to the original message. The simple logic is, imagine that you have applied 1 here and now the message is ending, which is our case. So once the 1 will go inside, so I need to apply something for the operation of the circuit, and now the 1 goes to the output of the second flip-flop. I need to have 1 more 0 applied. So I need to apply number of zeros such that the last message bit completely flushes out of this convolutional encoder. So in this case my constraint length is 3, so I will be applying 2 zeros. So now I have 1 here and 1 here. This one is the first input which I applied. This one is the second input which I applied. Now I need to append 1 0. So if I append 1 0 here, the output from the upper XOR gate is 0 because it has now 0, 1 and 1. So even number of ones, the output is 0. But for the lower bit, the 0 and 1 will generate 1. So again my output is 0, 1. And in the last clock cycle, you append 1 more 0 here. Now the previous 0 will go here and the previous 1 will go here. So the output from the upper branch is 1 and output from the lower branch is 1. So my final output is 1, 1, and here my sequence will end. So how many bits I am getting output? 8 bits. And what is the output? 1, 1, 0, 1, 0, 1 and 1, 1. Right? So this is how we analyze the convolutional encoder with reference to the given circuit. This is one way of analysis of the convolutional encoder. Your input just keeps on shifting, and once the last bit of input is applied and when it goes inside, I need to append number of zeros till the operation of the circuit is over. The last message bit should completely come out of the convolutional encoder. Right? So in short, if the length of the convolutional encoder is m, I need to apply m minus 1 zeros. So I am getting 8-bit output, which we have already calculated, n into L plus m. L is number of message bits, which is 2. M is number of shift registers, so 2 plus 2, 4, and n is number of adders. So 2 into 4, which is 8. So this is how the operation of the convolutional encoder will take place. Now, in this slide, we will see why the name of the encoder is convolutional encoder. Where exactly convolution is coming into picture. I have explained you the operation. Is it really convolution? So let's see why it is called convolutional encoder. So again we are referring the same encoder. When we talk about convolution, we need input and we need impulse response. Then input convolved with impulse response is your output. Right? So how do I get the impulse response of any system? I need to apply 1 and then I need to apply 0 throughout. Because what is impulse response or what is impulse signal? The signal which is present only at one time instance and it is 0 otherwise is your impulse signal. So when I apply impulse signal to this, whatever output I get will be the impulse response of the circuit. Now if I want to find out impulse response of this particular circuit, I need to apply only 1 1 here, and after that particular 1 I need to apply 0 and no more extra 1 is applicable because we are applying the impulse. Now there are two branches of the circuit. I have output coming from the upper branch and I have output coming from the lower branch. So we expect two impulse responses because this upper branch will behave as one particular root, one particular system, and the lower branch will behave as another root or another system. So if you have two such parallel outputs, we expect two different impulse responses. The impulse response is also called generating functions in the technical terminology of convolutional encoder. So let's find out impulse response of the upper branch. So I apply 1 here. We assume that the system is at rest. So once I apply 1 here, what is the output? The output coming from the upper branch is 1. The output coming from the lower branch is also 1, because these two are zeros and I am applying 1 here. So once I apply 1, the upper output is 1, the lower output is 1. Now in the next clock, this particular one, now the operation is not over. This one has to flush out this entire path of convolutional encoder. So in the next clock, this one will come here. Now when that one comes here, I need to apply 0 here. So if I apply 0 here, output of above upper branch is again 1, because see the connection 0, 1 and 0. And output of the lower branch will be 0, because now this XOR gate is receiving 0 and 0. Right? So I get 1 from the upper branch and 0 from the lower branch. Now I append one more 0, because that one is now available here. So if I apply one more 0 here, now see what are the values: 0 here, 0 here and 1 here. So the output of the upper branch is 1 and output of the lower branch is 0 and 1. So again 1. So after this, I found out the impulse response. So what is the impulse response? 1 1 1 for the upper branch and 1 0 1 for the lower branch. Again I repeat, I started by applying 1. So when I applied 1, the output branch generated 1. So I have written 1 here, this one, and lower branch has also generated 1. So I have written that one here. Now that one goes inside and we are applying 0 here. So once I apply 0, the output branch will still generate 1, which is this, and the lower branch will have 0 XOR 0, which is 0, which is this bit. And in the last cycle, again one more 0 is appended. Your 1 will go here. So upper branch will generate 1, lower branch will generate 1. So this is 1 and 1. So this is H1 of n, which is 1 1 1, and this is H2 of n, which is 1 0 1. So we got two impulse responses, 1 1 1 for the upper branch and 1 0 1 for the lower branch. These impulse responses, as I told you, they are also called generating functions. Now we have already applied 1 1 here and we got the output as 1 1 0 1 0 1 and 1 1. Let's apply the convolution and see whether we get the same output, which will verify our operation. So now what is my input? 1 1. I am keeping the input same because I have applied 1 1. So I am keeping 1 1 same, and let's calculate the convolution. This is a typical way to calculate convolution. So 1 1 1 is your first H1 and I am applying 1 1 here, and now 1 into 1 is 1, 1 into this one is 1, so 1 into this one is 1. So I complete this table, and now I take this first one, which is 1, then this 1 and 1 XORed. So 1 XORed 1 is 0, 1 XORed this one is 0, and 1 final one. So I get 1 0 0 1. That is output of convolution between your input and H1 of n. Similarly, if I calculate output of convolution using input and H2 of n, this is 1 0 1, which is H2, and 1 1 is your input. So if we calculate this, this is 1, this is 1, this is 1, and this is 1. So 1 1 1 1. And I am not getting 4 outputs simultaneously. What I am getting is output from the upper branch, output from the lower branch. That is output of one clock cycle. Then in the next clock cycle, again output from the upper branch and output from the lower branch. That is the second clock cycle. So I need to take 1 bit from the upper branch, 1 bit from the lower branch, 1 bit from the upper branch, 1 bit from the lower branch. So I will take this one, right, which is output from the upper branch, and this one, which is output from the lower branch. So my net output is 1 1. Then output from the upper branch, which is 0, right, and output from this lower branch, which is 1. So in this way I get my output 1 1 0 1 0 1 and 1 1, which matches with the output 1 1 0 1 0 1 and 1 1. So indeed we see that in this particular encoder the output really can be obtained using the concept of a convolution, right? That's why the name of this particular coding technique is convolutional encoder. So how do I get impulse response? To summarize this slide, we apply 1 and we keep on getting the different outputs, right? And then just keep on shifting your 1 and apply 0 because we are applying an impulse. So I just have to apply only 1 once, right? Now I get impulse response of upper branch, lower branch, and we get the output using convolution. Again, the point to be remembered here, your final output is 1 from the upper branch, 1 from the lower branch, 1 from the upper branch, 1 from the lower branch. So this approach is called time domain approach because we are taking convolution of bits in the time domain. Right? Now let's see the transform domain approach. So in the transform domain approach, we represent the generating functions or impulse responses in terms of its polynomial, and we also represent the message in terms of message polynomial. So let's see quickly how do I do that. So if I take the upper branch, upper adder, right? Now again coming back to this, so there are 3 connections. So input is considered as 1, then you have at this point a delay of 1 flip-flop, so this will be D, and at this point we have delay of another flip-flop, so this will be D square. So what is the convention? The input applied is 1, output of the first flip-flop is D, and output of the second flip-flop is D square. So your transform domain polynomial of upper branch or first transfer generating function is 1 plus D plus D square. So similarly, what will be the transform domain polynomial for the lower branch? 1 plus D square. There is no D here, right? So 1 plus D square and 1 plus D square, right? So if I consider this, so my upper branch is 1 plus D square, lower is 1 plus D square. Now I am applying the message again 1 1. Why I am keeping message same? Because we want to verify the output with all the possible ways. So the first way which we discussed is the direct operation in the of the circuit. In the second way we saw the concept of convolution, we got the same output. Now the second approach is transform domain approach, that we are verifying. So now message polynomial is 1 plus D, right? Now what is C1D? That is the code word polynomial from the upper branch. So it is 1 plus D square multiplied by 1 plus D, because convolution in the time domain is multiplication in the transform domain. So I am multiplying them. So if I multiply them, I get 1 plus D plus D plus D square plus D square plus D cube. Now D plus D will cancel out because it is XORing. It is mod 2 adder, and D square will cancel out. So what is the output? It is 1 plus D cube. So how do I write 1 plus D cube? 1, then no D square and only D cube. So 1 0 0 1. Now I get the code word from the lower branch. So it is 1 plus D square, which is the code word polynomial, which is the polynomial of generating function of the lower branch, 1 plus D square, and 1 plus D is again a message polynomial. So what I get is 1 plus D square plus D cube. So it is 1 1 1 1. Now again see, combining C1 and C2, what do I get? 1 from the upper branch, which is 1, 1 from the lower branch, 1. So my first is 1 1. Then I go to the upper branch, 0. And what is the bit corresponding to lower branch? 1. So 0 1 is the second combination. Then again 0 and 1, which is the third combination, and 1 and 1, which is the final combination. So what is my output? 1 1 0 1 0 1 and 1 1. So this is the approach of transform domain. So far we have discussed what is the need of convolutional encoder, how do I get code rate of the convolutional encoder, then what is meaning of constraint length, how many zeros we pad when we analyze the convolutional encoder, which is m constraint length minus 1, and then we saw the discuss the approach of circuit. We have also discussed the time domain approach, which is convolution approach, where we discussed why the name is convolutional encoder, and we saw another approach which is transform domain approach, right? So we'll conclude here. So this will be the first video of convolutional encoder. In the next video we see the different representations of convolutional encoder, right? I hope you have enjoyed this video. Thank you so much.